Hello everyone, thank you for joining me here on the Twitter Think channel. So in this video I'll be teaching you how to prove using the integrating factor to solve for a linear first order differential equation. And in my previous video there is an introduction to this video. You can look at it. I explain how to solve for linear first order differential equation using the integrating factor. In this one we are going to solve this question. The question says that prove that any equation of the form dy dx equal to L of x minus m of x of y is given by y equals 1 over rx, where r of x stands for the integrating factor, into bracket integral of Lx rx dx plus a. A here is the constant of integration, where r of x is the integrating factor, which I already said, given by r of x equal to exponential function to the exponent integral of mx dx, and a the constant of integration. So we are going to prove this in some few steps, and I want you to look at the introduction video if you haven't seen it. This will help you to get the basic concept, and subscribe to this channel if you have not. So let's see what we have today. So the first thing to do is to write down our equation. So we have dy dx equal to L of x minus m of xy. So this is what is given to us. We need to prove this using the integrating factor to generate this particular solution here. So in the first video, introduction to linear differential equation, we learned that the two variables L and M are two separate functions in terms of the variable x. So we have x here, two separate functions on their own. I will take an example under that after this proving in the next videos I will be doing. So we need to rearrange this equation because it's supposed to be in terms of dy dx and the variable y, then equal to the next function L of x. So this becomes dy dx, when I cross it to the other side, plus m of x of y equal to L of x. So this is the original state of the question. It's supposed to be like this. And then the next step is to write a statement that m here and L here are two continuous functions of the variable x alone. So that is all we have here. M and L are continuous functions of x alone. So now we multiply both sides of the integrating factor. IF here means integrating factor, E integral of mx dx, or r of x. So we are multiplying both sides of this equation by the integrating factor. So let's do that and let's see what we are getting. So we have E integral of mx dx times dy dx plus E integral of, so every part of the equation we multiply by the integrating factor mx dx, multiply by, and we have this. So we have m of xy equal to E integral of mx dx multiplied by L of x. So that is what we have. Now in the next step, we consider the left-hand side of the equation and we take the derivative of the integrating factor and the variable y. This is because I explained in the introduction video that the derivative of the integrating factor and the variable y will generate a result equal to the left-hand side of the equation using product rule. I've already explained that in that video. So we write a statement that it can be seen that the left-hand side of the equation is a differential of this and what? This. Then we write it down. So let me put down that statement. Alright, so the statement says that it can be seen that the left-hand side of the equation is a differential of the integrating factor IF and the variable y. Now, this is very important because when we get here, all we need to do is to consider the derivative of the integrating factor e to mx dx and the variable y. Why? Because when we consider the product of this and the variable y and we differentiate it using the product rule, the result is going to generate the left hand side. I've already explained that in the introduction video, so there's no need for me to do it here. So once you write this statement, all you need to do is to take the derivative of this and the variable y and equate it to this side. So this is giving us differential of y e integral of mx dx being equal to the right hand side of the equation, which is e integral of mx dx times L of x. Remember that L of x here is the function in terms of the variable x on the right side. Now we can now integrate both sides of this equation to get rid of this derivative and see what will happen. Now this is our equation. When we integrate both sides of the equation, what result are we getting? So we are taking integral of the derivative of y and the integrating factor mx dx should be equal to the integral of e mx dx times L of x. Now note very carefully, you write down every statement whilst you are proving this. So from this side, you write that integrating both sides of the equation, then you introduce your integral sign. Now this integral sign will take care of this derivative. So we are left with what? Y e integral of m x dx being equal to, now remember that we do not know the function L of x. So since we don't know the function L of x, we will repeat this side and introduce our constant of integration. So we have integral of e mx. Please, this is an integration sign. It's not an s, it's an integration sign. So dx dot L of x plus the constant of integration is what? Let me use a. So plus a. So now we can also use c depending on whatever you want to use. So let's use a because let's go back to the question. The question was using a as the constant of integration. What is our next step? Now let's go back to the main question. The main question says that the integrating factor e integral of mx dx is the same as what? R of x. So we can introduce that. So you can write something like, but e mx dx equals R of x. So now we substitute R of x into the main function and see what we are getting. So we have y times, wherever we see this, we substitute R of x equal to integral of R of x times L of x plus a. Now, do we get it? Now we can divide through by R of x to make y the subject of the equation. So we have y R of x. Let me do this. Out of R of x, giving us integral of R of x times L of x plus a divided by R of x. This will take care of this. So now we are left with y equal to integral of R of x times L of x plus a out of R of x. Now we are trying to prove the equation to generate this, so we have to manipulate the result we have to get this result. Whatever that we are seeing here, we just need to rewrite this equation in the form y equals 1 over R of x times this result. Don't forget that this is a fraction, so I'm just factorizing 1 out of R of x outside. Integral of R of x times L of x plus a. So we get it. So now this is now divisible by 1. So 1 times the numerator will give us this. And then let me put this down here. I'm just trying to explain for you to get the concept very well. So this time this will give us this. This time this will give us what? That. So your final answer, you can just ignore this step. There is no need. So your final answer is supposed to be y equals 1 over R of x. And you bring a big bracket, a square bracket, let's see. Then we can repeat. Now we have here integral of R of x times L of x bracket close plus the constant of integration. So that is it. We are done. So the question says that we should prove that the linear differential equation dy dx equal to this will give us the result 1 over r of x integral of L of x r of x dx plus a. Alright, so that is what we have gotten. You can choose to bring this variable here. Multiplication is commutative. I also left the dx function, so we can rewrite it y equal to 1 out of r of x multiplying the integral of L of x times r of x dx. So that is it, plus a. So don't forget that the ds function is, now why this dx? I was supposed to bring this, I actually forgot, I didn't put it there. So because we didn't integrate this, the right hand side of the equation, this side is times dx. We have times dx and times dx times dx times dx and finally times dx. So it depends on how you want to put it, but don't forget to introduce your dx, because once you integrate the right hand side of the equation, the dx will go away. So now this is the proof that y equal to 1 over r of x integral of L of x times r of x dx plus the constant of integration. So L of x here is a function in terms of the variable x that you can integrate if you have access to this function, and r of x here is the integrating factor. So the integrating factor can also be integrated if we have the result for what? The integrating factor. That means if we have the equation for m of what? X, then we can also integrate the integrating factor. Then the constant a, and then the result. So that is it for this one. I hope this was very helpful. We are just proving that it is possible to solve a linear differential equation with the help of the integrating factor. Thank you for joining me here. Please subscribe to this channel if this was very helpful, and see you in the next one.